Okay. Maybe we can zoom in just a little bit more. Because I got a bunch of slides. Thanks. So what we'll do is today we're going to finish off the bond graphs, and there is just a couple of elements that are missing. Those are transformers and also gyrators. I'll talk about transformers and how they relate to production in economics. And that will take us to the break, or maybe a little bit before it. And then I'd like to talk to what I'm calling mechanisms. So last Thursday, was it last Thursday? You gave a lecture on networks in economics. What I want to do now is look at economics from the perspective of mechanisms. These are the analogs of electrical networks. That's done quite differently, as you can imagine, but it's a very good thing, especially if you're a mechanical engineer, which I know all of you are, to go through that. Okay? Physicist, that's not really. He doesn't know much about physics. So let's get started.
I think that
one is permanently not working. Oh wait, what did I do here? Oh, that's the wrong button. So first, transformers. So let's first say what is the most simple transformer I got right here. It's just a lever. What does a lever do? You probably all know that. You press with one force, that's the effort here, the input. And you bring this thing in balance, you have to put another one. This is probably, if you go, this one goes down, that one goes up. No, also down, sorry. The physicists should know that. So, but this, due to the fact that this distance is not the same as this distance, those forces are not going to be equal. Okay? So this is drawn totally wrong, because this force should be bigger, and this force should be smaller, right? And with a lever, what you can do, of course, is you can translate a small force into a very big force. Right? That's what we all use them for. And that's the principle of the lever. It was known to the ancient Greeks. I think it was Archimedes who kind of figured out the math behind it. But I'm not even sure, but I'm sure they knew this way before, at least on the intuitive side. Okay, now, you can't just amplify a force without paying a price for it. So the price you pay here is that although the force is much lower here, you'll have to travel a larger distance. All right? So what you'll do is you'll go at a much higher velocity. That's the distance per time that you travel if you apply a force. It's done in such a way that the product of the two is a constant. And if you look at the product of the two, that's precisely the power. So what the lever is doing, power that's coming in equals to the power that's going out. So this I is for in, this is for out. That's all it does. So it preserves power. I mean, it flows the power through and it preserves energy, right? So, okay, that's a lever. And you have a lever in electronics, it's called a transformer. You can have one voltage drop, say 230 here. Nowadays it was 220. And then that comes out of the outlet here, the mains. And then you want to power up some, I don't know, a computer. Maybe that has 9 volts or something. So you've got to take a voltage drop from 230 down to 9. And in this little block, you know, you see these things at the end of your cord. There's a thing that's called a transformer. And it will drop the voltage from 230 to 9. And at 9, you'll be drawing can draw a lot more current than you will be drawing at 230. Why? Because the product of the current times that voltage drop is the power, and it's got to be a constant. Okay? Now these things work a little differently. You've got two coils. So these coils, they create a magnetic field. So here are magnetic flux lines. But they're so close to the other coil that the flux lines of this one will influence the flux line of that coil, and the flux lines of that coil may influence this one. So this is what they call mutual inductance. So this one is inducing a magnetic field on another one, and due to that changing magnetic field, you'll get the current flow. All right? Here, the momentum here is being induced. This force here induces a force, as it were, over there. You see? This is how this works. Okay? You should all know this. Huh? Yours, you have a question? Huh?
It only works with a fluctuating.
Alternating.
Alternating. Yeah.
Do we also
If you can do it with DC, you need a different type of circuit, right? You can't do it with this way, huh? Or you just do it this way and then you rectify it, you know.
Yeah,
you know what I mean?
afterwards.
Yeah,
So
afterwards, yeah.
you DC then change to AC
Right.
to the transformer and then back to DC.
But I'm told that they have purely electronic ways of doing it too, you know? That they
should work
just
with, the transformer also should work with DC. I mean, the mutual inductance, that still works.
But don't you need a changing current in order to do the so it won't work, right?
Yeah, but if you have a load, then it will.
Yeah, but the thing is,
the constant, you need AC.
the thing to do is you can't just get stuck that this is the only way to do a lever. You can do, I don't know, huh? I don't know what they do, right? Huh? Yeah, block and tackle it's called. Huh?
Yeah, but also with the transformer, it's the same as with the lever. If you push the lever once, then the other side goes up.
Yeah, that's true.
If you want stuff to happen, then you need to.
Yeah.
So with a transformer, you can put a DC current through.
Yeah, you can put a DC current. You'll get exactly.
Yeah, and it goes to the steady state.
Yeah.
So that's,
sure.
That's why you need AC to keep doing work.
He's got a good point. Yeah, it's exactly the same as this. Here, you just go once and you get this velocity and then thank you, right? But, yeah. So, if you have these things in the playground, you'll see it's an alternating current. It's a seesaw, and you call it in Dutch a wipbap, a wip gewoon, Dus it has to go up and down. Otherwise, you just go up, you get that child flying off to the moon. And I was saying hi to Buzz Aldrin. So that's right, he's right. But again, there are many ways to do this. You don't need a lever. You can need block and tackles and pulleys. Here they have other ways of doing it. Right? But the principle is very simple. You take power in equals power out. So you assume there's no friction here. Here you assume there's no resistance in any of these wires, you know. You also assume there's no elasticity in this thing. So it's a pure, it's not going to store any energy in the beam. And this one doesn't have any capacitance to store electric field in the transformer itself, supposedly, right? Okay. Otherwise, it's not going to work. Well, it will go work, but you just don't get what you call a transformer radius, which is it's called the modulus, which is a constant, right? So here I calculated as the length of the left side over the length of the right side. Here you have to look at the number of windings. Here it's drawn as if they're the same, but I mean there should be less windings here. And then you can look at the number of windings. And then that's just the constant, okay? And it's called the transformer modulus, or the mechanical advantage that you get. Now, in the bond graph, these two pictures are, and whatever they are, whatever is in here, and weird stuff of block and tackle or gears, or I don't know what you have, all of it is summarized by this transformer element. So it just says TF, there are two things coming in, there's one bond coming in, that's the power, that's split out into two conjugate variables. We've got two conjugate flows, right? An effort and a flow variable. and out comes something whose product is the same. And in fact, if you multiply this by this, you see the A cancels. Just obvious, right? All right. So, now what is this in economics? Now I wrote it down. I wrote down productivity. This is what they often call it, but really it's what they would call the marginal rate of productivity. Okay? And this, I just wrote down productivity because we're going to assume this is a constant, so this marginal rate at every margin will be the same, so you can just call it the productivity. And when they say rate here, they mean one product over another product, right? So you can see from this equation that the flow coming out, if this is a flow of goods, right, and we're just taking the mobility analog is equal to 1 over A times the flow coming in of goods. Now, what would be a really simple example of this in economics? I wrote it down here like retailer, right? So what you do, what does a retailer do? He gets in a big package with, I don't know, 1,000 toothbrushes. And he's going to sell them, you know, he pays, I don't know, so many euros for 1,000 toothbrushes. And he's going to repackage it. He's going to like open this thing up and put the single package there and go sell them by the toothbrush, right? So if you were not taking any profits and not doing any investments or anything, he's just passing this thing along, he will get a flow of toothbrushes coming, to boxes of toothbrushes coming in, and individual toothbrushes will be out, okay? And there'll be a ratio between them, which is exactly that, how many of these toothbrushes fit in this huge package, okay? Right, so this 1 over A would be a very small number in this case. That's just how it works out. And then the price, if he's not making any profit, he will have to divide the price by the same number, right? So he spent 1,000 euros for 1,000 toothbrushes, and he makes no profit or loss. He's just going to sell a toothbrush for €1, right? Okay? So, super simple. So this is just, so basically a retailer, or even a wholesaler who buys it from the factory, even larger things, you kind of can see them as a lever, right? And then just as a retail ratio, as his leverage here, his mechanical advantage. Of course, in the end, he has no economic advantage because he's conserving power here. There's some reality of this knowledge. Very hard to find somebody who's willing to do this for nothing. But this doesn't prevent us, and it's very important for you to see that, to look at these as ideal elements that we can then use, put in there. If you know the guy's taking a profit, you got to put an I element in there. If you know he's storing stuff, you got to put a C element in there. If you know he's dissipating his profits, you got to put an R element in there. You know, you've got to start building that. Don't try to say, hey, I need a transformer that does this long list of goodies. You know, you don't have it, right? And just don't say, hey, here the transformer seems to do this, therefore I'm going to assume a transformer with a ratio that does this. No, first try to figure out whether all these effects come from other linear elements. And only when you exhausted all the linear elements, and you're also convinced yourself that there's no point approximating for small, you know, in linearly, because that's just not going to give you anything precise enough. Then you'll have to move to nonlinear elements. Right? So I see a lot of times people have been cramming all stuff in all kinds of stuff in I element. You may be tempted to do all production theory in a transformer element. Don't do that, right? Keep to the linear theory for as long as you can, because we can solve the equations. All right. All right. Now, in practice, what economists do, they look at something that they call a production function. And this is what they write. They always use the same terminology and the same lettering, a big Y. These are macro guys. And for some reason, macro economists only use capital letters. It's like they put the caps lock on their keyboard and they can't get it off. Right? Micro economists only use lowercase letters. Right, yeah. As if the caps lock is not working on their typewriter. I don't know. You can, this is convenient. You can always see the difference. So they have something called the macroeconomic production function and a micro production function. And I have put them into one because we don't make the difference, right? And sometimes you see them doing that. So this is for micro and this is for macro, all right? So let's first do the micro part and then I'll do the macro part. This is what they call output, right? So this is what's coming out of that lever or the transformer. And this is what they call the inputs. This is the output, yeah? And these are the inputs. Now, one input you have, and that's the situation that you have, is just another commodity, right? So you'll take, suppose you're making cars, you'll take some steel coming in and some rubber, right? And then something happens, and out comes this car.
So you mean commodity or commodity flow here?
Sorry?
You mean commodity or flow of commodities?
Thank you. Yes. Yes, I mean the flow. Because in the lever, we looked at an effort and a flow. So here, this is also a flow. Yeah, that's what I mean, but that's what I did right. Thank you. Right? So there's a commodity flow of the commodity. Yeah? So many tons of steel a day. I don't know what these guys do. All right? And this thing gets transformed into some output. So in the simplest form, you'll see Y is some function of Q. All right, and we only have linear functions, so you do A times Q. And then you're back to Q dot, sorry. Yeah? So let's put a V here. For the velocity that pertains to Q, all right? And then we're back to the this situation. Okay? So that's the easy part. This is what they would call the input, right? So the process, the output. And I think this is very similar to how you look at stoichiometric equations in chemistry, right? We have Ozai here, which is the chemistry guy. It's very simple, very similar way of setting up a transformation from one set of chemical elements into another, right? And you can think of just a manufacturing plant as a transformative thing that takes raw materials on the one hand and just throws out products on the other hand. But both can be commodities, right? And then nothing wrong with it. Now, this is how microeconomists will look at it. They typically will also, they'll do something quite different. They'll look at budget sets and this. And they have a huge discussion, which for an engineer is somewhat surprising, whether these things really exist. Okay? So there's a whole group of economists that claims that production functions do not exist. And there is some kind of, they kind of assume, and then they all of a sudden they talk about themselves all the time, and then at some point they start talking about the engineer. So then the economics text, so if you look at Samuelson, will say at this point you go to your engineer and you ask him what the production function is. So maybe there were some economists who actually did that. And this engineer said, well, I don't know what you're talking about, like I'm doing this, I'm doing that, So the engineer wasn't able to come up with this production function, of course not, right? Because it's a very complicated process and not so clear how you would summarize everything that the guy is doing with this production function. So, and I actually think nobody's ever looked at it as a transformer. I'm not sure. But, so there was a whole discussion whether they exist or not. Now, I think the reason I'm saying it is because I want you guys never to get stuck on these discussions. It's not a question of whether it exists or not. The question is whether, when you're modeling a particular situation, whether you can use the idea, the analog of the transformer, in order to model the situation. All right? Yeah, sorry. Okay? So you can ask yourself whether levers exist or not. Now, maybe they don't. I mean, if you look at nature, and you look in a forest or something, and you do see a lever, I mean, maybe you do, maybe you don't, but yeah.
Your arm.
Your arm, yeah, but if you don't look at your arm, you just see a bunch of trees, right? But maybe the wings of a bird if you see it going by, right? But you know, but maybe your arm's a bit floppy, so it's not really a lever. I just don't want you to get stuck on these kind of things, right? Just see it as an analog of a particular type of very simple production. You know, you double your inputs, you're going to double the outputs, right? It's just a linear relationship, okay? Which may be true, or maybe not true, or maybe an approximation. All right? Now, classically speaking, this is not how it was looked at. Adam Smith was kind of the first, and he was in a line, he was in the Industrial Revolution. And you know, before the Industrial Revolution, life was a little bit simpler in a certain way. They only had one type of input to any production. There was only one type of production, which was farming, and there was really only one input, and that was the land itself. All right? So there was not much of a model. Right? The people who worked the land, they were kind of disposable slaves. The Romans had them as slaves, and here in Northern Europe we had serfdom. You know, there was some kind of people who were bound to the land. And the whole Roman economy was based on slavery. They would get them from Yugoslavia. That's where the word slave comes from. So, with the fall of the Roman Empire fell because they couldn't get enough slaves. That was one way of looking at it. But anyway, so kind of in the Middle Ages, there was this, I'm talking about the Western tradition now, in which all this was developed, some situation that there was just there was only kind of one properties class, and that was the inheritors of the Roman governor, and they were these feudal lords and barons, and they just had the land, and then they fought each other for the land. But if you needed some product like a helmet, you know, the one guy who made it, there was no production. Any production was in terms of meat that was done. And then with the Industrial Revolution, all of a sudden things changed. They started building factories, and the factory itself became a means of production. But the factories had to be manned by people that were brought in from the countryside. So the eldest son, you would get the farm, and the rest would just go to the city and start working in these factories. So to the land, they added two things called labor and capital. So there's a huge expansion due to this extension of two new dimensions. And they needed to deal with that, and Adam Smith was one of the first who kind of figured out that you just need to add these explicitly. Okay, so you could also put land in here, but for the capitalist, land is just not really, you know, there's not much. You just sit on land to build his factory on, and then, you know, and I don't care anymore, right? And then not for my garden, you know, lawn. He doesn't care about land as an asset per se. He needs his factory or his ships, something like that. Okay? So you get these things, and they call them factors nowadays of production. So the idea was, yes, of course, you need some commodities, some raw materials, but that's not what's interesting. That's not really the cost. The cost is all about the cost of labor and the cost of capital, machines. So this is physical capital, not financial capital. Now, we've talked about this before. These are a little bit different. So the stock here is not people, right? Or I just use here for convenience man because that's, you know. But you don't buy the people, but you buy a unit of time per people, okay? So what you contract out for, what your stock is how many man hours you have. So you can have 50 men working for 1 hour, or 1 man working for 50 hours, or 25 men working for 2 hours. It all kind of comes out to the same thing, all right? So that's the stock, okay? So, but this is a flow variable. So now you need to look at the flow of man hours. So say I'm looking at the flow per hour, you'll see that I'm buying so many man hours per hour, and it turns out that we just measure that in men. All right? The same with machines. So, but these are flow variables, right? Huh? So the integral of all the labor in dt, those are the man hours. Huh? Okay? It's a little confusing. So that's why these things like look weird, but they're really the same as this. Okay? So these factors of production are flow variables. You just have to treat them a little bit differently. So here is a graph I took out of Samuelson's book. So you'll see here, he puts labor, but this is in man hours per hour, right? But he won't say that that way. He would say people or something like that, right? So many people. And here you will see the total product. Now he doesn't mean the whole stock in big box, no. He means some flow of product. Okay? And then he says, okay, there's got to be some relationship. Now, I can linearize it and come over here. Now, they have all kinds of rules. They say there is something called diminishing returns here. So at a certain point, you got all this labor, but they're all running around using all the same machines, and they're getting in each other's way, and things are not going so well. So, you know, they draw it like this, or they may even do something like this. Then you say, now they're starting to quarrel among each other. You know, there are all these. Yeah, seriously, this is the kind of models they have. Now, we, of course, don't do that, right? If you take a real lever and you push hard enough, of course, this thing is going to bend, right? So you will never get with a real level made out of whatever material, never get a nice straight one. There's a certain force, you know, now, or a certain velocity you're going to put through, this thing is going to bend, right? So, but do you want to model that? No, it's probably either an elastic energy in this beam, or you should model it separately, right? So if you look at these production functions, what you should do, in fact, I took a look, I ended up not doing this in here, but I took a look at some of these transformer moduli. So you have these transformers, and these manufacturers, they plot how the modulus, so this will be transformer modulus, right, the slope. They plot how this thing goes by higher loads, and you'll see it doing about like this, okay? All right? So the situation is not too dissimilar, okay? Now, the other thing you should see here is that this is not really a lever. You see, if I go back to my lever here, the change is in the, if here's an X direction, here a Y direction, or here is a Q direction, Q, and here is a Q prime direction, okay. Right, some different good. Then both are changing only in this Q direction, right? So I'm taking toothbrushes, big boxes, and changing into toothbrushes, small boxes, all right? Here, this is different. So I'm changing not toothbrushes into toothbrushes, but labor into total product. So I'm going from a movement in one direction, mechanically, to a movement in another direction, all right? So you can't really use a lever for this, so that's why I drew this thing here. So you'll see there's a movement in, I don't care, labor here, and then this will be the product direction. And this thing will calculate your mechanical advantage. Okay? So pay attention to that, right? So if you have another thing here, this thing has to be at least in a commodity space of 3 dimensions. So you need V, K, and now this is the flow space, the tangent space where the vector goes. You need at least 3 dimensions. And this thing is some complicated mechanism, gearbox, pulley that's changing a flow. These are these directives into a flow in this product thing, okay? I'm not so good in mechanism design. Probably better than most economists, but I'm sure you can imagine in your head, you can figure out something that will do this. Right?
Again, probably the same score we had last week, that in the electrical grid you can easily put all these dimensions together, but in mechanics you're limited to 3D.
Yeah, well, this is exactly 3D, so it should be possible, right? So you get a movement here, and you have a movement over there. So I'm sure you should be able to figure it out.
And the y direction, the production value itself, should that be in an extra dimension or?
Yeah, that's what I'm. Oh, you're right. Oh, yeah, I'm missing a y here. You're right. You're right. So this is not going to work. So if I left out this one, I have a chance. That's right. Thank you. Thank you. Yes. And otherwise, I can just do some projections, you know? So I have something in 4D, and it will work, and then I can kind of take my four-dimensional sun and I'm blowing and project it down on 3 dimensions. That's the best I can do. You're right. Oh, that's right. Yes.
It's like the tutorial from the quaternions, where everything started moving.
Yes. But it's moving in a straight line in 4 dimensions, right? And
Maybe
then
with colors too.
yeah.
What?
Colors.
With the colors,
Yeah.
indeed, from 3 blue, 1 brown or so. Where
No, but just in general, you have 3 dimensions, and then on each coordinate you put for the value of the output function, of the production function.
I mean, the way to do it is the way you always do it. You kind of figure it out in 2 dimensions, right? And then you just generalize more abstractly. You know, well, that's all right. You know, just put it, you know, and you formulate it that it's nice and what we call covariant. So it doesn't depend on the choice of directions, and it won't depend on the choice of units. You just have something, and then you just write it out just more abstractly, you know, with vectors. You know it's going to work. And then you let MATLAB or whatever deal with it. And then when your results, you can graph them. You can graph them 2 dimensions at a time. That's what you do. But the point here is be careful, right? So keep careful when you look at the units, okay? Be careful that you have the right dimensional space to do it in, which I wasn't, or I was maybe careful that my care didn't even lead to anything useful, but you as well. And then be sure that you get on a nice linear part, you know, or that you realize that that's what you've assumed. Okay? And that's the best you will always do it. All right? So one of the advantages from having done some foundations in a really solid way, I think, is that these kind of things, I mean, production theory is like, I think it's a whole semester course in economics. And I just don't know what more there is to say, you know? You can look at these things and you can start reading it. There's a bunch of terminology, but ultimately, it all comes down to this ratio, this productivity. And well, they calculate, of course, all the different types of energy, all the different types of costs and stuff, but whatever. Huh? Okay. Let's see what I have for the next slide. Oh, gyrators. So, any questions from those of you who are doing this at a distance on this? Is this clear? I see some head nods going up and down. Huh? So, let's not waste too much time on that thing. Huh? But you would think that with IC, R, and the 2 junctions and transformers are basically there. In a sense, you are, because I think you can make, maybe Koen can correct me, but I think you can basically make every circuit this way. But there's a shortcut to get the full range of possible linear circuits.
No, it's the other way around. You can make everything with gyrators because 2 gyrators is a transformer.
That's right. You're right. That's right. No, that is correct. You know why that's correct? Because a gyrator is a flexion and a transformer is a rotation in the space, and you can make a rotation out of 2 reflections, whereas you can't make a reflection out of a rotation. That's the mathematical basis of this. So this is correct. So, but nevertheless, in most electronic circuitry, the gyrator has been able, well, people avoid using it, and they're able to do quite a
They don't exist.
They don't exist.
They're very lossy compared to transformers, if you want to make one. But the ideal gyrator doesn't really exist.
It was invented by a guy here at, it wasn't called AVI, he was an electrical engineer at Delft, here, a professor. He invented this gyrator. And this is the symbol he it's called a gyrator because we call a transformer a transformator, so it sounds like analog, right? So, and then the word went straight into English. So it was Professor Telligen who invented it. And but they're kind of mystical elements. You don't see much people using it, right? Anyway, let me tell you first what it does, and then in mechanical engineering we do have it. And previous theses have intensively used the gyrator. Not so much to, well, and they do that to switch price and quality, but let me get to that. Okay, so first, what does a gyrator do? Now, like a transformer, it's a power preserving thing. So the power coming in here, here's the power going out. Nothing gets stored, nothing gets dissipated, right? It goes right in. But this product can be preserved in two ways. You can do what we did is rescale the effort out of rescaled flows, but you can also do a funky rescaling, a cross rescaling. So you say the effort going out is a factor times the incoming flow. Remember before we said it was a factor times the incoming effort, right? So your want here, or your desires, depend on the incoming flow. All right? So this is not like these toothbrushes, where you just unpack them, and then your want has to drop. For a single, you want a single toothbrush a little bit less than 1,000 toothbrushes. So the want has to drop. Right here, it's a little bit the other way. It's the other way around. But nevertheless, if you multiply these out, the A just goes out, and you'll see it works. There's only two ways you can make this work. That's obvious, right? So that's why they say it's the only missing element. Now, the way you see this in mechanics is through a gyroscope. Everybody knows what a gyroscope is, right? It's just one of these discs, and it just keeps spinning around like a maniac. They're in your mobile phone. And what you know about the law of conservation of momentum, what this thing wants to do is it doesn't want to change its the axis of its rotation, right? So they got this thing here, and this is this gyroscope spinning. So he says no gravity change, it's not going to fall down, right? So this is just spinning all around this point here. And this is then the angular momentum. Now suppose what you do, so this is the input force. You put this input force in this direction, right? What's going to happen, the angular momentum is going to change. Because by putting this force in, you're going to end up putting a torque in this direction. So you're going to change the total angular momentum in this direction, right? So H dot is in this direction, right? Yeah, well, that direction, right? Positive or negative, either way. So in order to get that, you're going to get a force, like maybe it's in this direction, indeed, right? You're going to get, in order to create that torque, you need a force in that direction, right?
What force are we applying now?
Now you're applying this force, therefore you get a change in angular momentum in this direction. So what is going to happen? It's so you got to go. So this thing is going to tilt upwards in order to it's going to tilt upwards, I believe, right? Huh? You can see that, right? So it's going to tilt upwards, so you're going to get a velocity upwards like this. So a force in this direction will give you a velocity in that direction. There you go.
I know how the gyrator works. I quite see it from the picture.
Yeah.
I have seen
Right.
the demo with a bike wheel multiple times.
Right.
So,
Yeah, so you have to kind of think about it, but it's actually, once you see it, you kind of see it. You're sitting there nodding, yeah, sure. Huh?
Yeah, but it's really counterintuitive. So
It's really counterintuitive.
But the example with the bike wheel, it's the
Yeah.
The white wheel.
Yeah, so you can build one yourself. I once was to my son to Nemo. And I have this thing, you're holding glass, and you go like this, and you're going to realize that if you do a torque here, it's going to, check it out at Nemo if you want to. Huh? So, well, you can just build one yourself, take your bike apart. So,
don't do it just before an important appointment.
I mean, it's a little bit, now. But it's good, great cell.
But I don't understand the F2 because I understand that the rod is gonna tilt upwards.
Yeah.
But the F2 is pointing.
Yeah, so what is happening is the F1, that's this, right? And it's going to give you this V2, so the velocity in the two direction.
Yeah.
So, but this thing is not dissipating power. So you immediately realize that this thing relates to that. And this will be the F2, right? And this will be the V1. You see? So they will follow from conservation of power. So all you have to see is that this thing translates this to that, right? This is what this is saying. So F out is this velocity 2 is F1 divided by A here. And A is this L here. That's what happens. Anyway, you guys are young and you've done all these courses. I'm just old and I've forgotten it all. So I'm not going to explain to you guys whatever you know, right?
It feels like it's the other way around.
Oh, it feels like it's the other way around. No, not to me. I had some trouble coming up the stairs, you see.
No, I mean with that we've forgotten these things.
Yeah, but I'm still remembering some of that, right? Huh? Now, but take your time at home. You know that this is true, right? Huh? Take your time and just think it through. It's a fun exercise, right? So you see it's actually possible. And then when you think it through, you also realize it's not so obvious how you would apply that in economics. I mean, it's just a lot of thinking, right? But yet, we find, more often than not, people start, at the end, when they need to work it all out, they start sprinkling these gyrators around like very conveniently, right? So for instance, Emil is working on credit and interest, and the way it works is the interest, that is the stock variable, that's the Q, that's what you've accumulated, okay? And then the credit is the price you have to pay for the interest. So the credit is the amount of, there's the P, that's the price that belongs to having so much interest collected, right? So the whole exercise is about getting interest, and the price you got to pay for the interest is this investment is extending the credit. Now, in economics, that's just not how they think about it. They think as the money is the thing what it's all about, and the interest is the price, interest rate then, right, is the price of the money, all right? Huh? That's what they think. So the idea is that interest is the price of money. So it's for us, it's the other way around, right? So if you develop it following the rotational analog, you'll see that you have to gyrate it in order to start talking like economists would. Now, not all economists do this. There was a Swedish economist who came up with this idea that interest, because nobody knew what the interest rate was and why it's there, and then he said, well, it's just the price you pay for money. Now, if you do Hamiltonian mechanics, you know that what you call P and what you call Q it's your choice. You can do anything you like, right? So you can change the position as the momentum for the momentum position, right? You can do this. It's a canonical transformation. It's not done very often. And in fact, you'll see that in these analogs, so probably voltage is better, and not as an analog for force, but as an analog for velocity. And you're just changing the role of the two. You can do this, okay? And this is what happens, So for whatever reason, people want to see it another way around. You just put this gyrator in. You can even give it a ratio of 1, and all you do is we'll switch the role of price. And what's the price and what's the quantity? Okay. So it's good to keep that in mind, that you can just do that in order to make it fit the reality. So in Emile's research, it is right now current. I think Gilbert and Xavier, they had several gyrators to get it to fit better with the way, in Xavier's case, PwC would think about it, right? And in Gilbert's case, the way Ortec thinks about these things. So use gyrators just to get your model to fit better with the terminology that's used. Now that's my current thinking about it, and it's like all my thinking, it evolves. So if any of you, either now or in the future, has a great example of an economic gyroscope, then I would love to have it. But my feeling right now is that it's more something like, but it should be more, I'm not happy with the status quo of my thinking about this, because of exactly what Koen mentioned. The gyrator is the more fundamental thing.
Yeah, one way to look at it is if you have, for instance, a company that makes a product, and the amount of product that it sells goes up. So it's on the left you have the product space, and then on the right you have the stock space.
Yes. That
the value of the stock rises because the sales of the products increases.
Yes.
So that's the intuition behind it.
Yes. So maybe also like bonds, right? Where if the interest rate drops, then the value of the bond goes up, right? Right. Yeah, that's right. That's a nice intuition.
Yeah, or if the link between GDP and interest rates, for example.
Yeah. So one thing I always think about is, like, if I have a bond graph, I have here an I element, and I draw them often like this, right? Because I see here the flows summing up to 0, and I see here these efforts summing up to 0, right? Then one way to think about this setup is that I apply one analogy here and the other one there, right? So then I see these as prices, but then I see these also as prices, kind of the price I pay for maintaining this quality level, the desirability, right? So it's sort of other type of clearing. So what I like to do in my head, I gyrate sometimes between the description of the 0 junction with the C element and the 1 junction with an I element, because they switch the roles of the effort and flow variables, and otherwise are the same. So you can view them as kind of the same thing, but with a little gyrator in between. And I also believe that's kind of the origin of these two different analogs, because this is the electrical analog is built around the 0 junction because of the way they started off with electricity and then did magnetism. But the mechanical analog is built around Newton's law with this disjunction, the 1 junction, because they started off with Newton's laws and then derived the spring law, right? So you can also think of it as the difference between the Leibniz force and Newton's force, and maybe that's also a fundamental issue. To have completed my thinking totally. It's not really so important, especially in practical work.
In 2D, if you've got linear gear, and you connect it to
It's called
Two wheel.
tooth wheel.
yeah, but that's the round.
Yeah, the sprocket. It's called the sprocket. So this is the gear, and this thing here, right? This is called the sprocket. It's a gear and sprocket mechanism.
You
That's
connect the gear and the sprocket. In 2D, do we use the gyrator or the transformer?
No, what you do is you go from a rotational domain to the linear domain, right?
I believe this is also a transformer, right?
Yeah,
Yeah, it's a transformer.
because you're constrained by the.
Yeah, so
It works in the same way as
so here will be your torque, and your torque translates into a force, okay?
Yeah.
You're constrained by the material. So you cannot move at a different velocity than the rotation.
And that is possible with the gyrator.
With the gyro, you have a different mechanism.
Yeah. This is not a gyrator. So the angular velocity here gives you a linear velocity here, which is, if this is L times omega, right? Yeah? So here you see it's a transformer. I mean, this is a velocity and it's related to the other velocity. So you're done. Okay? Yeah.
And I still think of a
gyrator. Yeah.
It's a 2D gyrator.
Yeah, why don't you come up with that? So you got to get this length to be 0, and somehow you got to get it here. It should be possible. But you need this leverage. You need this extra dimension to create this silly leverage here, right? But if you project that down, and you just say that's a number here somewhere, then maybe you can measure. So you have to look at this thing from along here, right? So you got to put your eye here, and if you look at this, this mechanism will act as a 2D gyrator.
And a kernel.
Pardon?
A kernel.
A kernel?
Yeah.
I don't even know
Kernel,
what
right?
that is.
The thing they use with the steam engine.
Governor.
Governor.
You call it a kernel?
Both in politics.
Deze is een
A governor.
Steam governor.
What is that? I don't know what that is.
It's one of these things. It's a control mechanism. I don't want to take the because when you were talking about mechanical things, if you had good economic analogs, this is I would discuss them in class, but
Okay.
where you'll have to go to your mechanics class and come up with your 2D gyrators. All right?
It could be that it's.
But when I say I'm interested, you understand me.
Philosophy, rotational philosophy to.
So when I say I'm interested, I'm really interested in the good economic, But finding first a mechanical one could be helpful because then you can translate the elements into economic.
That was my force, etc.
Yeah. But okay, so what I want to do now is I'm going to switch subjects, but before I do, I'm going to take a break. This is a nice moment. And then we'll start talking about mechanism. I'm going to have some pictures here from a paper by a certain guy called Firestone. And he has a paper, it's right here, a new analogy between mechanical and electrical systems. And so if in the break you want to take a look at that paper. Go around. 1933.
It's not new.
No, that's precisely why I took it. This guy saw,
Such a shock guy.
you'll see the paper is all about the alternative way of doing an analogy between mechanics and electrical engineering. So you know how all the across variables become through variables. The analogy doesn't work very well. So he suggests a different analogy. And in order to do that, it's very confusing what happens in the mechanical domain? What is the Earth and what is this and what is that? So in order to do that, he was the first to kind of clearly write down how this analogy works and what the things are. And that's why I go back to it. It's also called the Firestone Analogy. So this is the first paper. And I read many other things, and I felt he is the only guy who was really getting it, okay? You see this more often, right? This old-timer, his drawings might look a little flunky, but he didn't stop thinking. A lot of people have great drawings nowadays, but they're hardly thinking, you know? So it is very old, but proudly so, okay? All right. Zo meteen praten we over die beslagen. Het is part 4. Okay, so now we're going to switch topics. I'm going to talk about what I call mechanisms. So mechanisms, to me, or linkages, you can call them whatever you like. They're the mechanical analog or networks or circuits. And the way we do it is often quite intuitive. You just learn how to have forces, you learn there, you get a free body diagram, and blah, blah, blah. And you get the right answers. And in this course, we've already met some moments that you just don't know what's going on, right? So what is a velocity? Well, then you're surprised to find out that the thing, nobody knows what it is relative to something else, that you need to define an inertial reference frame, and this is what we call the Earth or the ground. And what that thing is, it maintains a particular velocity, and this is what we're going to use as a reference point for everything. Okay? Now, this is very, if I say this, you'll probably get used to this, but what is an inertial reference frame, I ask you, in electronics, in electrical engineering? The ground, right? Okay. But does the ground have a constant current?
It has zero potential.
Right. So whereas an inertial reference frame has zero velocity, right? The ground, and that's our ground, right? And I put this down here. The ground in electrical engineering has zero force. Correct? Zero voltage, right? So it's quite different. They actually don't have a ground that has zero current or something. I don't know what it is, right? I asked some electrical engineers, they're like, what are you talking about? You know? So, and we don't really think of special elements that have zero force, do we? You know the point that has zero force? Right? No, not really. You can imagine that point. So you have this regular space and it's homogeneous and isotropic. The whole point about being homogeneous is you can shift space anywhere and the experiment is the same. So if there were a special point at which the force is zero, then it's not homogeneous because then the force will be something else somewhere else. Okay? But it can go at a constant speed. But you can't have some point being the zero point. You'll have introduced a spring, and you will have to have the relaxed position of that spring to be a special point, which is the zero point. And we just don't do that. Okay? Similarly, electrical engineers don't have a special element that gives a zero velocity, but they do have one that is a zero voltage, and that's the ground. You know? I'll do this, something like that. Okay? Okay, so this is a nice kind of wake-up call. Like, we got to be quite careful, right? Now, the other thing you have is, when you have these mechanical elements, here's a spring. Now, this is out of this article, so here's a very cute way of drawing a spring. And then when he draws a damper, instead of doing this, he draws a mechanical resistance. But whatever, we can sort that part out. But look at that, right? So the spring has two terminals. The left, which he calls the positive terminal, the right, the positive. A damper also has two terminals, right? And what about a mass? Where are the two terminals? There's only one terminal, and we just draw a force here, boink. Done. So where is the second terminal?
Your initial reference frame?
Yeah, exactly. So you see here, he draws this reference frame, he's got a little tower, and he says this is the other terminal. So the mass really, we draw it as it is here, but it really isn't. It's this entire element, you know? So you can't think of this force on here without thinking of a reaction force, right? We've learned this. Every force has an equal reaction force. So a force is really not one thing, it's two things, it's a pair. Okay, so there's got to be somewhere this reaction force, so I'll just draw it over here, okay? But this reaction force is against this thing he calls the Earth. All right, so this is against this ground. This is exactly right. But it doesn't really need to be. You could have another mass here, right? And then you wouldn't have grounded this mass. The mass would be floating. And there'll be another mass there, and they'll just be interacting with each other, and there's no such thing as an inertial reference frame. You know? Now, there's a way to think about mechanics like this, but we never do it, because it's just too complicated. It's just, it messes you up. It's called the two-body problem. I don't know, you're a physicist, you already know this is a serious issue. I don't even know if it's solved. Huh?
When we do planets, for example.
Yeah, that's the two-body problem, right? So that's two masses without an inertial reference frame. Now, sort it out. I think they haven't even, you can't solve it. Huh? I'm not sure. But if they solve it, the three-body problem is out of the question. Right?
That one is
a
solvable.
tricky one.
The three-body problem is
It's solvable. It's solvable, but without Hamiltonian and mechanics, it's undoable.
Undoable, yeah. It's
So with
undoable.
Newtonian, you cannot figure it out.
Yeah, so Newtonian, you can't figure it out. That's right. You need Hamiltonian mechanics. And that tells you already in Newtonian mechanics, it's like bond graphs. You need, you just kind of need this inertial reference frame to make it all work. Okay? And this is what we as engineers use. We don't use Hamiltonian mechanics where you can skirt around it, okay? So the way you're going to look at a mass is just slightly more subtle. It's also a two-element device, okay? Now, the way Newton taught us what a force was, it was like a flow of things, a flow of momentum, right? So Newton says this. This is his flow. Huh? So something is flowing. So if you put a force through a spring, you can think of this force as kind of flowing through here. And that's what this guy's vector is. This is not the F of a flow, but this is the big F of a force. Okay? Huh? So the force is flowing through there, right? If I look at this building, I'll see the roof. And you'll see it's just flowing through the beams into the ground. The momentum gets poured in by gravity. And it kind of flows like that to the ground in flow lines, and when it has to pass a corner, the flow lines are getting crunched up and the pony will break there. All right? Because the density of the force flow line is exactly what gives you the stress. So if you do statics, you get the stress tensor, and it will measure how dense these flow lines are. Okay? So the way we think about these things, and I'm sure medieval cathedral builders thought about it that way, by making their churches, Gothic churches, with these flying buttresses. They imagine this substance, and Gaudi, this famous architect from Barcelona, he built this cathedral called the Sagrada Familia. I think somebody even suggested that in one of the lectures, and you can see that he used the hyperbola. The hyperbola is a shape, right? You can ask him about that, where the flow lines go the most smooth. It's an arc. So you can see it's beautifully built and it's very stable, okay? The McDonald's M, I think, is also hyperbola, so it's very stable, so it will always exist and be able to sell your hamburgers under that sign. Okay. So, the picture of force that we get from Newton is that of flow lines through the element. So for the spring, it's very easy to imagine. For this damper too, it's just flowing right through. So you attach this damper, and you put a force on it here. The force is flowing through into the wall, right? And then you are pushing here, so you got your hand there, right? And there you are. And then what is happening to these lines? Well, the wall, you're standing on it, kind of, is the floor. So it's flowing like this, flowing into your body, right? That's what's happening. Okay? So everywhere there's an action-reaction pair. So here's an action-reaction pair. So the action-reaction pair tells you what flows in has to flow out. Okay? That's the picture we have of force. Takes a while to see it, and once you see it, you're okay. Right? Otherwise, you're just pushing around those equations. That's the picture of force. So the force is through. Now, we've looked at the Newtonian analog in great detail, and when we think of a force, economic force, it's in time, and so it's a flow, right, of money per unit of whatever good, right? So indeed, we see it also as a flow, if you look at it this way. Okay? So this money is the credit that you extend because there's a reaction, which is exactly the debit force, right? So the picture that evolves is a sort of flow of wants, and these wants are then measured by the flow of money. So we're not focusing in the mechanical analog of the flow of the goods, which a lot of people think is the most intuitive, but we're taking the concept of an accountant or a finance guy or maybe a businessman who's really only kidding. You don't care what he's selling, right? As long as the money keeps flowing, right? Okay? And then, now, how do we measure velocity? Well, velocity, that's the flow of goods, right, for us. It really isn't. It's quantity demanded, okay? So the quantity demanded, is that a flow? Or the way we did it was the principle of relativity. We said, okay, this is the zero flow, and then here I am demanding this. And what I'm doing is I'm looking at what the level of demand is here with respect to the market level. And if mine is higher than I'm supplying, and mine is smaller than I'm demanding, whatever. So I'm looking at the difference between the levels. Now, rather than focusing on the flow of goods, I focus on the flow of money, and I say at this particular flow of credit, the level of demand is high. That means people are buying a lot of apples, right? But I don't imagine it flowing. I just remember, imagine it as sort of a level, right? Sort of a thermometer, and it goes up, and it tells me it's the demandometer, right? That's what I imagine. Now, bond graphs do the other way around, and people find that hard. And they talk about the quantity demanded, which is more of a level thing, right? And then you start translating that in your head to the flow of goods, and then you get all mixed up what the effort is to want, right? Because that then has to be the level. But you don't have a level of want. You have a level of desirability, but not of want. The want is the thing that flows. My desires flow from me to you as buyer and seller. Okay? So, and my ground is the zero level of demand. So I'm saying here, this is the market, it's a lot of people, and this is the kind of the prevailing level of demand. Let me call that zero, right? And I will say this is the zero desire, right? Okay? So that's the picture I have. This picture can be translated into mechanics. Okay? And this is the way you do it. Now, the problem with this picture is almost the same. I mean, and Koen can tell you this, everybody gets mixed up with the signs in mechanical systems. It's very challenging to keep track of it. And the drawings we make it very hard. And I haven't read any paper, except for this one, and really deals appropriately with how you choose these signs in a systematic way. This guy had to do it because he came up with this other analogy, all right? So that's why I go here, and I want to go through carefully with you, not that carefully actually, but just point out to you that, you know, how to choose these signs. So look at these things what he's done. He's got a spring, he's got a damper, and he's got a mass, and both. He has a positive terminal, and he's got a negative terminal, very much like you would have in an electrical system. So the left side is the positive side, and the right side is the negative side, and he's done the same with the mass. So you see, you can put the left side here over there, so this whole thing is that mass, and there's a positive side and a negative side. Now let's see what he does with that. Oh, I put this in between at the last minute, and that's why it seems to me now that it's coming out of nowhere. Because here I wanted to summarize that story about action is reaction. So let me do this slide, right? So remember, here is our mass with our positive terminal and the negative terminal, and then I can apply a positive force to it. Okay, that's what we would call a credit. This is F prime. That then gives rise to a reaction force in this direction, because that force is going to flow through to there. Right? That's going to extend this distance here. Okay? So it's going to make this distance bigger, right? And the rate at which this becomes different is bigger. But it is as if the Earth doesn't like this. It is as if the Earth is going to pull back and say, no, I don't want you to accelerate. I want you to keep going at that same rate. You know? So it is going to pull back this way. All right, so this force gets transmitted through the mass to the Earth, and the Earth is saying, no, you're not allowed to accelerate. Okay, it's a weird piece of thinking that happens to be true if you think of it as a sort of anthropomorphic thing. But I believe, if you look at it from an economic perspective, it's much more intuitive. So this guy is being credited, but it is as if he doesn't want to be credited. He needs to be debited at the same time. He's going to prevent being credited by debiting at the same time to come back into balance, okay? So this company just can't credit some money without handing it over to the shareholders who want their piece, and they need to be debited, okay? So this credit force gives rise to the debit force on this side, okay? Go back, or let's go forward to that then. You see, he has a bunch of things. I'm not going to go through all of them, but you will find them in the paper, and you can see that what he is doing here, he's being very careful of how the signs are. So you have now this flow through 2 points. So here's a point in this empty space. But what you have to imagine that this force is flowing through this empty space, like a sort of gravity. Who cares? It's a reaction force, okay? And it can flow this direction or this direction. And in this direction, we'll say it's tensile, so it's pulling it apart, right? This is what we call a compressive force. So the two directions are tensile and compressive. All right? And then we'll have signs. So this will be a positive direction, I believe this negative on the other way.
So a compressive force tends to push terminals apart.
No. Oh yeah, puts it apart. Sorry, yes. Yes.
That sounds counterintuitive. Compressing sounds like you're bringing things together.
Yes, and it sounds very counterintuitive. However, so this is a positive thing, and that will tend to pull this thing apart. But I agree with you. This sounds a little counterintuitive. I have to say, the whole thing is.
So is it
The
possible?
force itself is compressive, right? If this was positive, and
Yeah.
it goes that way, then force is
So the force wants to pull it back in.
Yes, the force wants to pull it back in, right? I have to say, I find this.
Spring force, and you're extending it, and the string is.
Let's look at this spring here. I think that's better. The spring tension, right? The displacement differences must therefore be positive at the left terminal, meaning that as seen from the left terminal, the right terminal must have moved in a positive direction. So the way you look at positive is you take the positive terminal, you anchor that to a wall, okay? And then if the negative terminal moves in this direction, then you get tension, right? So if you had anchored this one on the wall, then this will be a negative displacement. So you take every element, take the positive side, anchor that to the wall, and look at the motion of the negative terminal. You see? That's the trick. The mass is just kind of screwy because through empty space you get the reaction force. That's what I believe is happening. Is that right in your eyes? I see you nodding, right?
Yeah, I'm trying to get it. So the spring one I get, but
Yeah. Yeah, the empty space is just a hard one, right? But forces just go through empty space. Reaction forces, gravity forces, all this stuff, you know? That's a weird thing that nobody ever was able to figure out, but that's how it is. I mean, that's how a conductor, right? Empty space. Or a complete resistor, whatever you want to call it. Right? So this is the spring and compression. And let's go a little bit on. Our resistance is the same, right? So you take this damper and you anchor it, and then this will be positive. Right? And then here's the mass. Mass with acceleration difference of sign shows must be in tension. So this mass is in tension. Yeah? The right terminal is accelerating towards the right. So tension is, this thing is being credited. Compression, acceleration of the show must be in tension. Okay. I get myself confused. The point is, when you draw out, you always do it right. But then when you have to translate it carefully to economic engineering, just be, be very careful that this is the positive, the negative, how you anchor it, etc. All right? That's really my message, I believe, at this point here. So here, if you work it out, here you can put, this is two masses and a spring and an amper, right? So he's just got this is the spring, and then this and this. And then for the rest you have to draw nothing. I mean, there's nothing. So it's a two-body problem connected this way, so it's going like, still. All right? So he immediately goes ahead and he adds these two little towers to calculate, to see that these are, what these masses are. Then he's got everything at two terminals, and you can easily see that here the velocities are going to have to add up to zero, right? Because these things are not moving with respect to each other. So if you put this whole thing in series, you will see that the velocities add up to zero and the forces are the same. Okay? So it's like putting them all on a zero junction or something. In fact, if you make a bond graph, how many one junctions would you have here, Jose? So here's one, right? This is the velocity of this mass.
Yeah, but you would also the reference. So
so I do one. There the V is 0, and this one, and V is V1.
And then between the spring and
here's another one, right? You could probably eliminate that one, but this one you need to have this one, right?
And then you don't need the last one because you already have the first one.
Yeah, but you could put it in, and it's another velocity is 0, but you don't need this one. They usually cancel those, right? So if you draw a bond graph, you go figure out all the points where you have a particular velocity.
A unique velocity.
A unique velocity, yes. Huh? But zero counts.
Because if you generalize it and you put it on skates,
Yeah.
then it is not zero, but could be 1, could be 2. You've got a moving reference frame.
Yeah. So you put this on skates, and then you have another one that's the real inertial reference frame.
And then you've got the center of the universe and then
Yeah.
the center of the...
Yeah, so that tells you also what is the issue of taking this reference velocity. You see, you gotta make a choice. Otherwise, you start, making your model of real estate, and you're starting to model the center of the universe. You don't want to do that, right? So
Unless you want to really hydrate it.
free real estate over there. First one to get there.
But you also see that at that zero velocity, the momentum is also going to be zero, right? Because P is mv, so the price will be zero. Does that mean that, in the end of the day, you can't add something to it? No, of course not. You got to see that that's where you calibrate it, the price is at, and you're looking at everything, right? What I like about this picture, when you go through it, it just carefully works out positive, negative, positive, negative. You see the force going through the series. You see the velocities across, right? So you see all the ones going from here to that guy, and they both are in connection to the market, right? Providing the reference. And there you are. So this is a completely complete mechanical series system, all right? And why do I say this is a situation of competition? Because not anybody has a monopoly on this flow of goods. Anybody can yield the goods. The market can, right? Either at this location or that location. This guy can, right? Here are the 3, 1, 2, 3, 4 sellers. But these are the same. They're just operating at a different location in the graph. All right? And they share the total velocity among them. Right? So this is like an Edgewood box. You can see that you're exchanging these goods, but in the end, the goods don't disappear. So whatever is going on here, this market has to buy up, right? And it's getting the right ones in order to do so, right? And the force gives you the flow of money, right? The flow of money goes right through there. Okay? And the levels of demand, you can just read them off here. So they're not going to be the same. At a certain point, this way we're going fast. This guy is hardly storing anything now. Now this guy may be doing absolutely nothing, because this guy is selling everything to the market. Okay? So you can read it through. So, Oza, you're the one who said often, like, okay, I don't really like this picture, but what I'm trying to do here is to show you that it's just a total legitimate way of looking at it from a very different perspective. But the problem is just that when we draw these things, you leave out all this, and then it becomes really confusing. Even if you put it in, it's still confusing to me. Look at it. I was all prepared for this lecture, and he says, well, I don't want to say why is it tensile. I'm going, well, I don't need that now. But when I see this, I have the confidence that if I think about it long enough, I'll sort it out. Okay? That's why this is a good paper. Okay? You guys see this? Yeah? So here you see a system in parallel. So how many one junctions do we have here? Well, I guess we have one for this velocity, right? One here, right? Yeah, this one is the same as that one, right? And how many zero junctions?
4.
Yeah, I think this isn't this one, right? Huh?
No, but
These share the same.
because the 0 junctions are why we think every unique force.
Yeah, right. That's right. So 1, 2, 3, 4.
And then 1 and 3.
So this is 1,
Yeah, they are already labeled, so on the left.
Oh, yeah, right.
And those masses, do they have to be the same?
No, I mean, they have the
Why
same
do you have
velocity.
then one junction?
Well, because they're connected.
So for example, you have this. You just
yeah,
connect
so
it.
Yeah, it's just connected. Right?
You could lump them together as two masses, just one mass.
Yeah, but you could lump two springs here also, right? If there was another spring here, you can lump them together. Huh?
Yeah, of course.
Yeah, and then they're twice as stiff, right? That's right.
But why can you take the masses together but not two springs? Oh, there's just one spring, that's it.
It's a string and a resistance.
Yeah.
I mean, they're all in parallel, but there's a resistor, but you have two masses. You see, so he nicely draws it in parallel, like these. Huh? So all these things have the same velocity here. You see, once you do them in parallel. And when they're in series, they all have the same force. That's all that's going on here, right? So you just add, huh?
But then here, would you get rid of, because we said that we have 4 zero junctions, but would you get rid of the zero junction at 1 and 3 because
Yeah,
they
that's
have
what I
4
meant.
0?
Yeah,
Oh, yeah.
Yeah, so then you would have only 2.
yeah. Like here, you can get rid of that. Right? Yeah, that's right. And you do, so you never see these. Huh?
But when you build a skeleton, you put them, and then after that, you take them out.
That's what I'm doing it. Or if you don't have experience enough, you don't do it. Or if you don't even know what you're doing, you typically don't, and then you hope for it to come out okay. Huh? But the point is, if you think about it, you can see that there's a lot of simplification that you just kind of already just kind of throw in there just because of the experience you have, you know? And it's just, and then you do this, but then you don't get any more what you did, and you look at an electronic circuit which turns this around and makes this a lot clearer that these things got to be there because they only have zero junctions that disappear, you know? And then you go, hey, it's much easier, but it really has the same problems except the opposite. Where are the one junctions that, huh? Okay? So this will be a monopoly situation because this whole guy is one guy delivering this, but he can pocket, if this is one person, he pockets all the price changes. So you can't distribute your demand anymore over different suppliers. It's just the same. And here you can distribute the level of demand. So take a look at that paper. I guess the reason I don't want to say too much is just because it's in there, and I just want to alert you to the principles that's going on, and it's really nice to see that you can look at a system from either analogy, right? So, but nevertheless, this is what we were talking about last Thursday, and you can see that. Well, you know that in an electrical system now, the ground is going to be where the force is zero, and then the flow variable is going to be across, and the cross variable is going to be flow. So what you see here is a common current. And the common current, that corresponds to this common velocity. All right? And you can, in the same way, you can see now that the voltage drops, they all have to add up to 0. So let's call it F force, okay? Call the current a V, otherwise it gets so confusing. All right? So we just flip everything. Now if you work it through, I didn't do it there, but you can do it here. You call the inductors, you call the mass. You'll see that the effect really is that you're just summing the masses, and this is what I believe Ruma was pointing out on this one over here. You can just add these two masses, right? Because they're just linked together. Here, you can add all 4 of these inductors because you're going to push the same current through. Or they actually will push through the same current when you put that big voltage drop over it, right? That is a better way of reasoning. But you know that the mass is the inverse of the elasticity, right? So what you're also a way of doing it is that you're summing the inverses of the elasticity to get the inverse of the total elasticity. So just a trivial statement. Okay? You follow that?
Yeah, but I'm looking at the next step.
Yeah.
Then you have the masses or the inductors in parallel in the electrical case.
Yes.
But then we say they also do this for resistors, for example. Then they calculate some sort of net resistance, so the 1 over R total or 1 over RP, and then they use the same trick.
Yeah.
But if you go back one slide, how would you do that for masses in the series? Because then you would have some sort of 1 over mass, but that feels strange because because from experience so if you have 2 resistors in parallel and you calculate what the net resistance is, it becomes lower than both resistors, both of the resistances.
Right.
But then if you do that here for 2 masses, you get a mass that is lower than both of the masses.
That's right.
And then you get, so it's like you
We don't get necessarily lower. You get 1 over m is equal to 1 over m1 plus 1 over m2,
yeah, but then
right?
if you calculate m is lower, is smaller than both m1 and m2, right?
Unless, suppose that they're both 1, right? Then you get a half, the 1 plus 1 is equal to 1, so so they're the same.
1 plus 1 is 2.
It's 2, yes.
Yeah.
2.
And then you get m is a half.
Wow.
And then you get m is a half. So, but then in the top case, you would then get some sort of net mass that is lower than both of the masses.
Yeah, interesting, right?
What is that?
Well, it's like, if you put these masses together, then of course to push it, it's going to be twice as
Yeah,
hard.
exactly.
But now you put them in parallel, what happens is it's like a gas, so you come in there with your finger, this thing has a huge mass, but you're feeling nothing. You're just pushing one molecule and then another, so you're picking them off one by one,
It's like you have water, a body of water, and if you want to move the whole body, it's very heavy. Let's say you have a water balloon and you can pinch it, so you only have to move the water that's in front of your the line of the, so that mass is lower than the mass of the.
That's right. So I think of it like, suppose you have this like here, right? And then this mass, and there's all these little molecules, and this whole thing is going to weigh something, right? I come in here with my finger, all I hear is this one little thing, okay, boy, fine, right?
But now the question is that less mass than if that's one molecule and another?
I'm
You
sure.
have to do less work because they are parallel, so you can go through some of them and not through others.
Yeah,
Same as with resistors, you can, if they're in series, you have to go to each of them step by step, or you can just pick one and let the other go.
So that is why it's less than the total, but with a 1 over, it's also less than one individual. And
Yeah, but I mean,
Ja, dus die vervuilingsweerstand of the net resistance, it becomes lower than each of the resistances that you have.
yeah, no, I understand that. I mean, the way to do it is just go through the calculation, right? I mean, and then you follow this. So you see that from this equation, you'll find this, and you just work your way through it. This is how you calculate these formulas. But I find it a good question. I always thought of it as just a gas what you're pointing through. The real answer is we never do it. It's I think, and it's difficult to rig it up, whereas it's extremely easy to rig up a bunch of capacitors in parallel. It's very hard to rig up a bunch of masses in parallel. And the problem seems to be the fact that you see this spring that has 2 loose ends, okay? So you don't necessarily have to anchor this to the wall, right? But the way he defines the mass, it's always anchored to the wall. So you have a little bit of a problem. You need to solve multi-body problem to correctly do this. You see what I'm saying? Huh? So I find it too hard to imagine, personally.
Yeah, I find it too hard as well.
Yeah, and I think the problem is that, okay, you see this spring here? It's just floating between this, and there's no problem. But you see these masses, they're not floating. They're always anchored to this, okay? So it's hard to put them in parallel because all of them are, or series. Because how do you put them in series? You'll have some in the middle here that are floating.
Yes, I was just about to say my problem is with the series.
Yeah, so you can't get them, you can't. So the way he defines a mass is always with respect to the inertial reference frame, because that's what Newton did, right? But you should be able to define it, as some floating thing without an inertial reference frame.
You could define it with respect to another mass, and it's just floating.
Yeah, but we haven't done that. The laws have not been formulated by Newton in that way. You could do it with Hamiltonian mechanics, but not in Newtonian mechanics, okay? You said it so yourself, so the two-body problem can only be done with Hamiltonian mechanics, right?
No, the two-body problem can be done with...
3 bodies.
All right, so say 3. So I have 3 bodies here, right? I'm stuck. Huh?
But I think the important part with the 3-body problem is also that it's in 3D.
Maybe, but it's all related. It's just what I think the problem is that the way, if you look at, from his perspective, the way he does it, you see that the mass is always defined with respect to the inertial reference frame, the force. And that's the source of this problem. That's my current thinking of it. And then when I want to put things in masses in parallel, I tend to just switch to electrical engineering, and it's trivial. But I think this is, it's a source of confusion also for me to think of competition from a mechanical analog, because it's hard to put masses in series. So you just hit on a sore note here, So I'm just not going to be able to satisfy you entirely, but I mean, if you have a way of, if you know by next Thursday how this goes, we'd love to hear from you.
Maybe Max, the other Max knows.
Max Broekman.
Yeah.
I mean, most of this stuff that I figured out for this lecture, I would venture to guess that from this department, 95%, I never thought about it. Just do it, It's on board. So this is where we stand then on this. So, but yeah. So, okay, but I do want to point out, so why did I put this here? Just because when you build these big networks and you need to put, these are masses in series, which are inductors in parallel, right? You'll see that competition, rather than doing this complicated, then it becomes the masses, so the inertia is harder, but the elasticity is easier, okay? This is an important point, okay? Elasticity is easier. Elasticity is what the economist uses. So he used the inverse of the mass. So from his perspective, this is the the natural way. You're just adding up the elasticities. Whereas from mechanical engineers, this will be the most normal thing. This is what we call the law of conservation of mass, all right? This is what they would call the law of conservation of, I don't know, elasticity or something, and only about a law, right? So you can calculate the total elasticity of a competitive market. You can also calculate the elasticity of of a monopoly market, but you just got to go through this 1 over is 1 over trick. All right? So that's something I wanted to point out, which, especially, for Max Brookman, who is doing these kind of things, interesting perspective. Quinton is looking at value chains and how they distribute. And we're going to look at cross elasticities, which was my next slide, but I want to reserve that for next week. Okay. So the nice thing of these configurations, so masses in series, inductors in parallel, is that the elasticities add. Okay. So for economics, this is the more useful situation. And the irony has it that this is the one that's hardest to imagine, as we're finding out for us as mechanical engineers. So maybe by next Thursday or Tuesday we'll have some deeper insight on why this is the case. Huh? What's going on here?
We know that the replacement resistance in electrical circuit is the 1 over, but does it also count for the replacement inductance, if that is?
Yeah, because you have to see how you calculate these things.
Also the replacement capacitance.
Yeah, because all you do is, you go back to this equation, okay? Yours, first of all, it's true. Second, don't freak out about these equations. Here is what you know, right? So just start filling in. What is VI? That is PI divided by MI, you sum it to 0, you get a bunch of equations, you calculate the total P, right? So you posit a total P, which is M total, right? Times V total, right? You sort it all out, huh? P total is 0 here, then you sort it all out and you get that 1 over, you get your equation, okay? So why does it flip around? Precisely because these formulas flip around, So here is the sum of 1 over, and the other is, because here you'll see this 1 over coming in. Huh? So it's not so, he called it a trick. That's not the right thing to say. It's just a direct consequence of this. You learn it as a trick, but this is how they would derive it. But they do it for resistance, but you can do it. As long as this is the case, then you find that it's this sum of, no, this is the 1 over law, you see, because you're summing velocities, and this is just this law, because you're summing those accelerations, forces. Okay?
Mm-hmm.
Yeah, so don't think too deeply about why that is.
It also holds for example, in mechanics when you have 2 springs in series. That is also, you also use the 1 over law.
Yeah.
Right?
And the resistance.
Yeah, so you put 2 springs in parallel, it gets twice as stiff.
Yeah.
You put them in series,
it becomes
it
less.
becomes, 1 of the total, and I think that's much more floppy, huh? But much more elastic, right? You put 2 dampers in parallel, of course it's going to, huh? You put them in series, it's going to be much easier, right? So you get the 1 over law. It's the same with masses. It's not easy enough to imagine. You want to accelerate 2 masses in series, okay, you get the 1 over law, and then you want them in parallel, well, it's the plus law. So, in a sense, there's something.
Yeah, but the 2 masses in series confuses me.
I know, but, so that's the last step. I think we should see if we have some time on Thursday, and otherwise, we can address it
Because
again.
intuitively, it doesn't get easier if you have 2 masses in series.
Yeah, but
It doesn't get easier to push them.
But it should.
According to this formula.
Yeah, so it's a question here of,
Maybe it's not physically possible to put 2 masses in series because they're always connected to the ground, like you said.
that's what I
And
think
then
the problem is.
they're-
How do you connect them?
That's the problem. I think that is the problem. The way Newton defined the masses with respect to inertial reference, this guy follows that, you're stuck. You need to have a theory of masses that float, and we don't have it, right? But maybe that's where I think the problem lies. If I looked at my intuition, So we find it difficult. So I have to imagine this gas. I tried it once and then my brain exploded. This gas, but I'm not standing on anywhere. You know, I'm part of this gas because as soon as I'm standing on somewhere, I'm pushing from the ground. So then the whole thing is not working. So I'm part of this gas, and somehow, you know, I'm kicking it around, and, you know, or whatever.
And masses should have the same velocity, but a different force acting on them.
It's 5/3, half past. So I want to end this lecture.
It's 5/3, half past.
3:05. Huh? 5 minutes over time.
You could have saved yourself a lot of trouble if you just said that.
You know what? I could have saved myself a lot of trouble if I had gotten rid of students like you. Can you put the recording off?